Right, hello and welcome. This is the first kind of like proper video that I'm going to do. Now, just want to apologise just about this a little bit here. I haven't quite worked out how to kind of sort this out yet. So at the moment we've just got this view of PowerPoint because it's not properly downloaded. So I might use something else in the future, but we'll stick with this today because, well, why not? So anyway, today we're going to be looking at half integer spins, what we actually mean by the term spin, how it's come about, and a few other things. But let's crack on with the first slide. If I can, there we go. So the first slide is just a bit of a recap on the different types of elementary particles and how the universe is kind of made up. So this kind of really, depending on obviously where you are, this is kind of one of the first lectures that I'm going to give at the university level, but this is referring back to A2, AS level maybe, depending on what you did, but obviously it's just a bit of a refresh, and to be honest some people might not have done it anyway, so it's worth going over. So you have two types of particles in the world. You either have hadrons or leptons. Okay, so the hadrons, hadron comes from the Latin word heavy, and that is known as a heavy element. It's called a heavy element because it experiences the strong interaction. And I'll go over all the different forces in another video. But anyway, so that's one group, and that is subdivided into two other groups called baryons and mesons. And they're only defined by their quark structure. Okay, so a baryon will either have 3 quarks or 3 antiquarks, and mesons will have a quark and an antiquark pair. Okay, so examples of baryons are protons, neutrons, for example. Just think of some others. And mesons, well, obviously you've got your pi meson, you've got your k meson, you've got your pi 0 meson, whatever. I've drawn this basic quark structure. I've not drawn it, you probably can't see it there, depending on if you can actually see it on this video or not. But anyway, it's just you can have a look yourself if you can't quite see it on this video. But essentially it is about the strangeness to do with quarks. It's labelled as such. Now there are many different types of quarks, okay? The ones that you may have learnt about at A level are slightly different to the ones I'm going to go over now. Okay, so what I'm going to do is pause the video and just change the view of it, and we'll get cracking. I'll go through the different quarks structure. Okay, so what I've done here is I've just listed, excuse me, just listed out the quarks. Okay, so this is just a few examples. There are a lot more, but these are just a few I've listed here for you to see. So these are kind of, they're put into two brackets or boxes, whatever you want to call it. These are called the nominal quarks. These are called the anti-quarks. So I've forgotten to write the word anti there. Excuse me. Now, just like antiparticles, the magnitude of the actual particle is exactly the same. Okay, so hopefully you know what I meant by that little equation there. But the actual value is slightly different. Okay, it's in the opposite direction, i.e. different charge. So I'll just go through what these quarks mean on the nominal side, or normal, whatever you call it. Okay, and then I'll go through obviously the antiquarks. So what we've got here is the two groups. Okay, these numbers on the bottom of each set of letters, okay, if you want to call them that to start off with, they are simply the values of the charge. So basically this plus 2/3 here represents a plus 2/3 charge. Okay, so that all these quarks here, the up, charge and truths, all have a charge of plus 2/3. Okay, so say for example these quarks here, actually I've already explained it, sorry, never mind. So this U is called the up quark, that C is called the charm quark, This is called the true quark. And now over on the negative third side, we've got the down quark, the strange quark, and the beauty quark. Now the strange quark is actually got a strangeness of -1. That's because the strangeness can change in a decay or through weak interaction, which obviously you should be aware of, as one of the main examples of that is beta decay. Okay, so you could prove that for yourself by substituting in the quarks instead of just using, you know, proton turning into neutron or neutron turning into proton, whichever type of beta decay you're doing. Okay, so that's kind of an example of that. Right, so the antiquarks are actually just, like I said, the same but the opposite charge. Now, the only confusing thing about the antiquarks, which I'm just going to go over now, because obviously you're all intelligent people, so you probably know this already. What we've got here is the anti-up quark. That is not a down quark, okay? Do not consider these as true directions, okay? They are just names. They're confusing names, but at the moment we'll just call them names, okay? So, like I said, the anti-up quark is not the same as the down quark, okay? And you can quite clearly see that from the charge. If you compare the charge, it is not the same, okay? So they are not equal. And similarly, the anti-down quark is not the up quark. Okay, so that's basically all I wanted to say on quarks. Like I said, I have kind of put a proper quark structure on the board, or say board. So used to have a board at home. This is pretty crap, but on the monitor. Okay, so that's all I really wanted to say to quarks. Now, in terms of leptons, I'll just move over and I'll be back a second. So, as I was saying, so just to explain the quarks, just now I'm going to move on to the next little bit. Obviously the other type of particle that you have in the world is a lepton. Now, kind of like everything's the opposite here at the moment we're talking about, the lepton is kind of the opposite of the hadron in the case that it experiences the light force, because it is not light, for God's sake. I should put that as an outclip, but I'll leave it in for your enjoyment, the people that have made it this far. So leptons experience the weak interaction, okay, they often decay. They are primarily elementary particles. Okay, and examples of such are the electron, and the muon, which is a heavy electron, and the tau. Okay, so they're examples. Now, a bit more on elementary particles. Now, what do we actually mean by elementary particles? Well, elementary particles are basically the smallest thing that there is. The way of thinking about this is, an example of a hadron is a baryon, an example of a baryon is a proton, and the proton is actually made up of quarks. You could say, in essence, that if you were comparing like for like in terms of what's at the bottom, then the quarks are the elementary particle in this case, like the electron is an elementary particle. However, obviously, quarks are not a particle in themselves, they're just something that makes up a particle. What I'm trying to get across to you is that they're both kind of the lowest state of their respective fields, i.e. the lowest state of the hadron is the quarks. Okay, so the elementary particles. Sorry about that. So, anyway, as we were saying, the lepton is kind of the bottom rung of that ladder. Okay, in terms of that, obviously the electrons are not made of any smalls. Hopefully, I've said that enough times. You've got it in your mind and you're sick to death of me actually saying it. So, anyway, moving on. The next thing I want to mention, excuse me if I refer back to my notes of what I'm going to say and when. So, now we've covered basically everything that you really should be aware of, okay, especially if you've remember your AS physics. We're going to be moving on to the next kind of bit. I know this is the true nature of what I'm actually trying to get across to you today. It's going to help us understand what we actually mean by the term spin and how we apply it to certain situations. Okay, so like I said, there's hadrons and leptons. Okay, there's another classification that we can look at, and this classification of particles is not necessarily as fundamental as hadrons and leptons. You can kind of think of this in the way that it's describing what something is, okay, whereas the actual hadrons and leptons were describing what we actually see and how what there is in the world, okay. Whereas these two things I'm going to introduce you to now are just describing what those things are, if that makes sense. So it might go into make a bit more sense when we start to actually have a look at some of this stuff. So the two classifications here, we've got fermions and bosons, okay? Now, the way to think of these, I'm going to say the definitions that are kind of like textbook definitions, if you will. So fermions are classed as things that make up our world, and bosons are the force carriers. So basically, bosons cause the fermions to move, if you're thinking quite literally. However, in a different way of putting it, fermions are actually the basis, the foundation of the universe, okay? They're what you touch, whereas the bosons, the force carriers, are essentially the exchange particles, if you like. If you, again, remembering you exchange particles from AS physics. Now, at this point, could go through in the entirety of the AS physics particle spectrum, but maybe it's something that is not for this video. Okay, so anyway, they're fermions and bosons. Okay, so the next thing I want to mention is what the hell does this have to do with anything at all? Okay, so, oh yeah, sorry, so, actually, no, let's go back to that. So fermions, we give examples of these, actually, before I continue. So, fermions, as I said, they are things that make up our world. So, again, these are the idea when it was mentioned about elementary particles. Okay, so you could say fermions are things that make up our world are the elementary particles, so your electrons, for example. Whereas your bosons are the force carriers. Now, I mentioned about them being in terms of the force carriers. So, sorry. One sec. Sorry, so, anyway, as I was kind of stopping myself saying, bosons, examples of those are photons and gluons. They're kind of the exchange particles, as I was saying, but I wasn't quite 100% sure. Okay, so the next bit, going to go on to actually talk about a little bit about spin. Okay, so what I want to do, before I just kind of say what it is, because a lot of the time people just kind of say what stuff is and just expect you to know it. And obviously, as you're well aware, one of the differences at uni is they want you to understand where stuff has come from, which is great. So I thought I'd do a bit of the same here. Right, okay, so how was spin actually invented? Spin was invented through Dirac, is that right? And basically, he was looking, when they were hypothesizing this, they tried to use quantum mechanics to kind of explain it. But at that particular time, when Dirac was looking at quantum theory at that particular time could only really explain non-relative, I can't even say the word, relativistic, no, relative, well, basically, when you get close to the speed of light, you know, like the layman's terms, how it all starts to get weird in terms of, you know, time slows down, time dilation, this, whatever, because they're travelling at the speed of light, so the light is, you know, for you to see something and the light bounces back to you because you're travelling at the speed of light, it kind of affects it. But that'll be for a different video. But anyway, so going back to this idea of what Bose... God, I've managed to go off track here, sorry. So going back to how did they actually came up with it. So anyway, at that time they only knew that really about quantum theory, and it wasn't really kind of explaining, there was a few gaps in the knowledge of quantum theory, okay, because you could only apply it to situations such as the one I've just described. Okay, so a lot of the time certain parts of the equation weren't actually balancing, and as we know, okay, that everything kind of has to balance. Laws of conservation, you've got conservation of energy, charge and mass, and you also have the conservation of spin. Okay, now obviously you need to know what spin is for this, but basically that was a little bit of an introduction how they kind of like were coming up with it. Okay, so they were having these equations and it didn't quite balance. Okay, there was some kind of loss of, the best way of putting it is energy. Okay, so this kind of like, in terms of relating it back to what you did at college, you might have done stuff where when you did beta decay, for example, your lecturer or teacher, or whatever you want to call it, at the time probably just said something as simple as they just came up with the neutrino, okay, to explain the loss of mass, okay, which is technically true, but the real reason is to do with actually the invention of spin, and the invention of spin helps categorise what a neutrino actually is, because going back to that idea of there is a loss of mass, okay, for there to be a loss of mass, you can't just make that up with including a random particle, because there are many other laws that go along with that, okay, such as the conservation of charge and the conservation, really law kind of thing, but conservation of the lepton number, okay. So stuff like that, you can't just make a particle and it just happen to fit, okay. You've got to think a little bit logically about it. And in thinking a little bit logically about it, one of the things that it came up with is it must be, say for example in beta decay, it must be some variation on an electron, okay? Because obviously in beta decay they knew, depending on obviously which way around you did it, if it was a neutron to a proton, for example, obviously that's beta minus decay, but so they knew that there had to be a proton coming out, okay? They knew that there was an electron coming out as well, but that didn't balance. Remember, they didn't know about the existence of the neutrino at this time. So there was, again, quite rightly, as your teacher says, a loss of mass, but there was also a conservation, if you could say it like that, of the actual lepton number, okay? Because you had an electron, but you had nothing to balance it with, okay? And as, going back to that again, you obviously have the side of the equation now where you have to conserve the charge. Well, this particle cannot be charged, okay? Because the charge is balance, you know, a neutron going into a proton, and then also coming off with an electron means the total charge before it went into the system is 0, and the total charge coming out is 0, okay? So it must have had to have been some kind of variation of the electron, but again, it doesn't have to have a mass. Now, that's all well and good, you already know that. But one of the other reasons it had to be an electron, okay, was to do with this idea of spin, okay? Now, going on to this idea of spin, okay, I think I probably better explain at this point what it actually is, because if I go any deeper, you'll be going, what is actually spin, okay? You explain this thing, and you still haven't actually explained what spin is for a start, okay? So, what is spin? Okay, so, well, spin is actually not what you think it is, okay? When you hear the word spin, you generally think of twirling around. I could do it now for you. Do a little twirl and just a dance. And there you go. I mean, that is what you anticipate spin. But something I'm going to actually come on to in the actual lecture notes when I'm going through some of the videos for this course, okay? The way to think of it is, you may have seen temporary models, if you want to call it that, of the atom, okay? And in those models, you probably will have seen something about just the electron simply just going around the nucleus, okay? Well, it's actually spinning on its own axis. And it actually, well, imagine that for the moment, okay? It can't, because it's actually a point particle, and a point particle, if we assume something to be a point, it can't rotate on its own axis, okay? But we actually call it spinning on its own axis something about intrinsic angular momentum, okay? Now, this intrinsic angular momentum of an electron is what generates this term spin. Okay, now you can have positive spin and negative spin. You can also have up spin and down spin. Okay, now what I'm going to do, okay, just now, is I'm going to kind of pause the video and show it on the A4 bit paper I've got over here. And what I want to do is almost kind of describe what spin is. Now, I could look it up on here, but I don't think it's actually a very good explanation. So what I'm going to do is pause the video now and move on to the idea of what actually is spin diagrammatically. Now, I'm just going to explain what spin is. Now, I know I did mention about fermions and bosons before, and I will be coming back to that, but just for the moment, this is the way I want you to think of spin. Okay, so essentially, let's try and angle this so I can see what I'm doing. Okay, so you may have seen, obviously, this is your kind of general idea of what an atom looks like. Okay, very, very basic. You've got a few points here. You know, you've got your nucleus and you've got your electrons. Okay, but it doesn't actually, you can't really imagine it as this. Okay, what I'm going to try and get you to imagine that as, okay, that's right to a certain extent, because obviously in this particular state, okay, you've got the electron going around the atom, but you've also got to imagine that the electron's actually spinning on its own axis. Now, that's for basis. We know it actually doesn't, because it's a point particle, and a point particle cannot spin on its own axis. So the way to imagine it is, if we go back to that idea of the atom, okay, what we have is this wavelength of the electron when it's going around the atom. And the way I kind of like signal it is something like this. And I'll explain what this is and why this is. Okay, so I mentioned about what spin is. So spin, as I mentioned, is intrinsic angular momentum of an electron. Okay, now obviously it doesn't have to be an electron because of something I'm going to explain in a second. Excuse me. But this is the way of thinking about it. If we've got this idea of spin, I'll kind of explain what it is, intrinsic angular momentum. Now, I'm just going to, for a second, take part from this so I can explain what it is. Fermions and bosons have integer spin. However, some of them have half integer spin and some of them don't. Some of them have full integer spin. So how do we kind of define that? So fermions are dictated as such because they're what make our world, as I mentioned before, but these also have a half integer spin. Okay, so that's what they are. And bosons have what we call a full integer spin. Okay, and what do we actually mean by this? Okay, in terms of what's the difference between half an integer spin and an integer spin diagrammatically? Okay, so if I just draw the same thing again, okay, you've got center. Okay, so what I'm going to try and do now is I've drawn what I need to. I'm just going to explain it. Okay, so if you can imagine the top as the example of a fermion, okay, and the bottom is an example of a boson. Okay, now as I just told you there, that the fermion has a half integer spin and the boson has an integer spin. These diagrams aren't actually perfect in terms of they're not scientifically correct, but it's the way that I'm trying to get you to explain it. Okay, so anything that has a half integer spin will be having a wavelength which is asymmetrical, i.e. half of it is kind of got this wavy pattern to it, okay, and it's not the same as the other half of the atom, which is kind of straight, if you know what I mean. And the boson has a symmetrical wavelength. It's the same on both sides. Now, what I mean by this, I can't really draw it because this is stationary, but basically the way of visualizing this is these pulsates, okay, i.e. when the electron's going round, it's not going to stay at the same point all the way around the curve. Okay, so what these do is the wavelength of the electron is represented by this kind of wavelength as it goes around the atom. Okay, and this whole, I mean, the shape stays the same, but actually this comes in and goes out. Okay, so if you imagine this expanding and contracting, but whenever the time it's expanding and contracting, it's still got the same shape to it. Okay, so therefore the wavelength is always going to be asymmetrical. It's not going to be the same on both sides. Okay, but you have this wavy pattern and you'll have a circular pattern. Okay, and that, remember, as I said, is for a fermion, whereas this, the bottom one, is for a boson. Okay, and that has, as I mentioned, a integer spin of 1. Okay, and that's because this is symmetrical. So as this pulsates, this is pulsating as well. Now, what I'm talking about pulsating, remember I'm talking about the wavelength going, because the electron does not follow a pure circular path. Okay, it's not ideal in the sense that it doesn't stay in the same point in the atom. Okay, now you can refer to this as, if you want to have a quick look at the Bohr atom, okay, which kind of represents this by this, it's very similar idea, but because it doesn't quite stay in the same particular part of the curve, it's therefore got a different wavelength. Okay, so that's kind of what I'm trying to show here. So that's the idea. Okay, right. Is there anything else? Yeah. Okay, so that's all I really need to show you. Sorry for the paper view. I'm just going to go back to the normal video in a second. Sorry. So anyway, going back onto the next thing I want to talk about. I want to go into something called the Pauli exclusion principle. Okay, which was actually created to try and help the understanding of spin. Okay, so one of the principle states that two fermions, basically elementary particles, cannot be in the same position at any one time, which is basically the explanation for the electrons being on a single path inside the atom. However, there are examples of this. Okay, so sorry, actually I'm not going to say the examples now. If we relate the Pauli exclusion to the bosons and fermions, then the fermions obey it, but the bosons don't. Okay, because obviously they're not elementary particles. They can be in the same quantum state at the same time. Okay, i.e. the same point in the universe, or have the same trajectory numbers. Okay, so right, going back onto the actual what it means in terms of the fermions. Okay, so examples are light, for example. You can have many photons, okay, going from a laser. Okay, so they're bosons, sorry, and they all can be at the same point and directed frequency. Okay, so that's the laser. However, fermions can actually be in the same point at the same time if we apply our idea of spin. Now, taking the idea that spin can be positive or negative, okay, as long as it cancels out, it's okay. We're not adding too much spin, we're not taking away too much spin, because you can't add or create stuff that wasn't there before, essentially, is the way you want to think about it. Okay, so they can be in the same position if their spin is in the opposite directions. Okay, so therefore their spins will cancel out in terms of an equation. Okay, so that's one area where you can look at the exclusion principle being kind of like turned on its head. Okay, but that essentially is the Pauli exclusion principle, which, as I said, was helped to explain the theory of spin. Okay, to be honest, I think that's as far as I kind of wanted to go with this. So what I've got here is this kind of this PowerPoint, which I can email over to you if you have any questions about what I've gone on about today. It feels like a lecture. I've also got lecture notes. Why do I keep saying lecture? I've got notes on basically what I've gone through today, so if you were making notes and you missed something, just leave a little comment on this email and I'll get straight back to you within 2 years, and I'll email off the document. Okay, so sorry it's not been the usual display of video. I might adapt it for future videos, or I might put it on and then take it off and change it again, put a new type of video on. I'm not 100% on that yet. Okay, so thanks very much for watching. I hope you've enjoyed it. If you survived this long, well done. If you skipped to the end, I'm sincerely disappointed in you, but I understand. Okay, so thanks for watching, and we'll see you in the next video, if you're still alive, which maybe you are. Hello, you in there somewhere? So, sorry, that was a bit weird then, but thanks for watching, and we'll see you very much. Thanks for watching, and we'll see you soon.